Okay, I am really delighted to talk about this paper with the Northwestern team, Jeff Ely, Annie Liang, and Chaofeng Wu, who is a fantastic PhD student of ours, who's been really the driving force behind this project and who's here. So we have a lot of research on complexity mattering for decision problems. We know that it makes it harder for people to make good decisions. We focus on a different aspect, which is complexity in strategic environments. So here, complexity is not something that is determined by some external force. It's something the players are steering in the course of the game. In the situation where this is a huge deal, and people think about it hard and in a sophisticated way, is chess. And we use that for that reason, and also because there is a huge amount of data that we have on how people play chess. So if you open a game theory textbook like Aumann's, you learn about Zermelo's theorem, you learn about games of finite games of perfect information and a few other conditions like chess and tic-tac-toe. And what these games have in common is from any position in those games, either one side can force a win or the other can force a win or both can force a draw. And you can tell which by looking at the position and thinking hard enough. Some chess positions really are like tic-tac-toe situations, but others aren't. And the standard theory of chess misses that distinction. What we do is first we use a large data set on chess to try to understand how complexity matters. In fact, how good is the basic game theory model? What is it missing? So we see that it's missing something. We're going to find that people do in fact do worse in terms of playing correctly in complex positions, consistently with the literature that I've put some papers from here on the single agent kind of view of decision problems, and people have even explored this in chess, this last paper. But we find that beyond echoing that message of the literature, we're able to actually study something new about when players choose to make things more complex. And we study that in the data. And at the end of the talk, I'll tell you how we're building a model to think about this in a strategic way. We're building a game theoretic model to do better than the standard game theoretic model of chess, to study this choice of whether to simplify or complicate. Okay, so let me tell you about the data part. We took 10 years worth of chess games played on the second largest chess platform. We restricted mainly, there's a few other small restrictions that I'll not talk about because of time, but we restricted to endgame positions, which somebody has brute force solved. So the true values, the maximum values of these positions are known. They're called table-based values. And we got 1.9 million positions, each appearing in about 100 games in the data. So this is a huge data set we downloaded. What do we do with this data? We construct a data set of ordered pairs where the first entry is a complete description of a position. So this tells you everything that you might, everything that's going on the board and who's to move. And then the second thing is what actually happens on average in that position. So in our data, we look at all the games in which that position occurred. We code the outcome of each of those games as 1, half, or 0, depending on whether white wins, draw, or black wins, in fact. And we call yi the average game outcome across all those positions. And we frame this as a prediction problem. So if you're like a machine learning person, I say, look, predict for me what will happen if this position comes up on the board. So one prediction is, and we're going to score by squared error of loss. So one prediction rule is classical game theory. We have Zermelo or Aumann, and they have faith in rationality. So they'll tell us, I predict that if this is a win for white, then white will win. Okay. So that's the table-based prediction. Table-based is the name for these known values. So let's look at how that does. We use a performance measure taken from Hindenburg, Kleinberg, Liang, and Willenathan, which says, okay, it's hard to parse these mean squared error numbers in an absolute sense. Let's fix the benchmark. We're going to fix a standard benchmark that really no prediction should do worse than. It's just the material value benchmark where you look at the board, you compute the standard total value of each player's material, and you say the player with better material is going to win. Not such a great rule. It gets you a mean squared error of 0.06. And when we compare that with table-based prediction, table-based does 74% better. It takes away 74% of that error, gets you 74% of the way to a perfect prediction. So game theory is not bad, but it's clearly leaving something on the table. And what we do then is we throw in a huge bag of features that you can see from a position, like what pieces are on the board, Are they in corners? Is the king in check? Are pawns about to promote? And when we add all those features, we think that we get 16% more prediction. That is, we get up to a total 90% total we get 90% of the way to perfect prediction. So other features than the ones that the classical game theory model thinks about matter. And if you talk to a chess player, as we've already discussed, one thing that matters is complexity. And so what does table base miss? Well, it misses something about complexity. We could now go and develop a full theory of how to assess the complexity of a chess position. We're not going to do that. Instead, we're going to come up with an intuitive, a simple heuristic for defining complexity, which is we're going to call a position complex if it's not what it seems to be, that its intuitive value differs from its true objective value. And so how we do that more precisely is we train a very simple machine learning classifier, a short decision tree, to use features that a chess player can see, like are pawns about to promote, stuff like this, and predict based on features like that, whether this is a win for white, a win for black, or a draw. Then for each of our positions in the data, we also know the table-based value, and we're going to call a position complex if those two things disagree. So these are situations, so a position is called complex if these two predictions are different. Some interpretations, so one is the one I told you, the game theorist and the simple algorithm disagree about what will happen. Or you can think of these as irregular positions, where its table-based value is different from other positions that look like that to the classifier. Okay. And so this is an example of such a position. If you glance at it, it looks pretty good for black. And our classifier also thinks that, but it's a draw. It's not easy to pull off this draw. And when we look at the actual distribution on play, which this definition has nothing to do with, but in actual fact, 85% of the time in this position, black wins. And so our classifier is picking up something about what makes a position unintuitive. Let's do this exercise more seriously in the data. So we do this for all the positions. We look at positions that are simple in our definition, that are complex in our definition, and we look at how well table-based, the standard game theory account, does at predicting the actual outcomes. And we see that the error of table-based is a lot bigger, about 50% bigger for the complex position. So for complex positions, standard game theory does worse. And maybe more interestingly, players make more mistakes in complex positions, echoing the message of the literature. If you have a position that's the weak code is complex, so what's a blunder? A blunder is a move that changes with table-based value. Say I had a forced win, and now it becomes after my move, it becomes my opponent can force a draw. That's a mistake for me. I shouldn't have made that move. That kind of move happens a lot more, 80% more in complex positions. So our notion of complexity seems to track empirical behavior. Okay, so this is all good. So we've seen many ways in which the standard game theory model is not succeeding. It's missing something about complexity, but real chess theory, not our chess theory, but real chess theory is not missing it. So this is maybe the most famous American chess coach, Bruce Pandolfini. If you've seen Searching for Bobby Fischer, the coach character, I think, is loosely modeled on him. And he has this advice: if winning, clarify; if losing, complicate. This is an advice that's given to chess players. So let's look, and so we're going to call this the Pandolfini doctrine. Let's look at the data. So we divide positions based on whether the player moving is losing, which means it's table-based loss for them, or winning. And we see that then we look at situations where you have a move that makes the next position complex in our classification or simple, and we find that losing players are they're 3 times as likely to make the position complex. They take complex moves 3 times as often. So they seem to be behaving as if they're following the Pandolfini doctrine. Okay, and these are, by the way, I haven't shown error bars on anything because you couldn't see them if I did show. A lot of chess data. Okay. So we've seen that the standard game theoretic model of chess is incomplete. People systematically deviate from it, and the deviations are predictable from complexity. And people seem to be doing something strategically that's responsive to complexity. At least it's consistent. The behavior is consistent with that. People are following the Pandolfini doctrine.
In that previous slide, how much of that gap can be explained by the fact by perhaps the hypothesis that in a losing position, it is very commonly the case that the best move happens to make the position more complex?
Great question. So we're looking at moves that were both preserved, that we leave those out of this data set, where you have a complex and simple move, both of which are theoretically okay for you, preserve the table. Should have said that. Okay. So, so what are we going to do now? We're going to develop a theory to think about. So we're unsatisfied with the standard theory of chess. We're going to develop a very simple model to think about this complexity decision using game theory. Okay, so let me tell you the model. It's ambitious given the time, but I think we can do it. So it's a very simple game where two players take turns moving. And there's an evolving public state that has two dimensions. So this is a very toy model of chess, to be honest. So there's two dimensions. One dimension is the advantage of the mover, whether the mover is in an advantage or disadvantaged position. So think of this as whether the person moving is table-based winning or losing, and we leave out the draw. And the second dimension of the public state is whether the position state is simple or complex. So whether, which is just a binary thing that we introduced, binary abstract dimension. The moving player can choose a complex or simple move, and that determines the complexity of the next position. And then after you make a move, and this is crucial, nature is going to flip a biased coin to decide whether your move was a blunder. So how do we interpret that? You know, when I'm in this position, I have a great idea for a complex move, but I may have missed something in analyzing that position. And it may actually be that I've just hung a piece and now after that I lose. And so the probability of that depends on, you know, what kind of move I'm trying to make. It's going to be more likely to blunder when you're trying to do complex stuff. I could tell you more about that. But if you blunder, you lose immediately. And then you give the move to the other player. There's one more feature of the game that I'll introduce when I show you the game tree. So I'm going to tell you about this game again in a game tree, but I basically told you the whole structure of the game. So I'm going to show it to you and tell you the secret thing I haven't told you. So let's look at a kind of a play of this game in a game tree. Let's say we're starting with the advantaged player moving, and the position is complex, and this player makes a move. Let's say that she chooses a simple move. So that leads to a nature node where nature creates a blunder with some probability. That probability, so the index S tells you that she made a simple move and from a complex position. So the blunder probability depends on both those dimensions. And then, you know, if she blunders, the game ends with her losing. If otherwise, the game continues with the next player moving, the other player, the disadvantaged player moving from a simple position because she made a simple move. I could have also done, you know, there's a totally analogous tree from a complex move with only the blunder probability differing. Now now our disadvantaged player has the move, exactly the same tree. So everything is analogous, but note all these blunder probabilities depend. Now they're starting from simple positions. And now I'm going to tell you the last Harry.
Does it make sense to assume that people know who's advantageous, who's disadvantaged?
Very good. So this is a huge and kind of offensive simplification in the game that it's a public state. It's a little bit in tension with this idea of blunders, and we don't like that. We shouldn't believe on that. So same exact thing. The one feature that I'm going to tell you about now is this termination feature, which is important to give a meaning to advantaged and disadvantaged. So after the disadvantaged player moves, nature has one more, even if that player, called he, doesn't blunder, the disadvantaged player might immediately lose. So there's a parameter tau called the termination probability. And if that event happens, then the disadvantaged player loses. You can interpret that as the advantaged player sees how to pull off a win, sees how to force a win, and after that, there's nothing the disadvantaged player can do. Okay? So that's the whole game. And after this, let's say our player made a complex move here, didn't blunder, the game didn't end, then we go back to a node just like that. So it has this recursive structure. Okay. So I'll tell you our main result about. So this is our game that we're going to use to study chess, and it's kind of the simplest model where you can ask when the Pandolfini doctrine makes sense, because it has all the ingredients that kind of I think he's trying to think about at a basic level. And I need to make some assumptions. So I'm going to assume that the blunder probability is lowest when you're making a simple move in a simple position. It's higher when either your move or the position is complex. Now, I'm going to give you sufficient conditions, so we can't have these probabilities be too different. The probabilities of a blundering when making a complex move from a simple position or a simple move from a complex position need to be not too different. Okay, so I'll tell you why the theorem is surprisingly not trivial to prove. But under these assumptions, we can prove the following mathematical version of the Pandolfini doctrine. Okay? In any equilibrium of this game, where the I guess I should say any Markov perfect equilibrium of this game, where the disadvantaged player plays simple, regardless of the complexity of the position. The advantaged player also has to play simple. So it's never going to happen that the disadvantaged player is sometimes doing complex moves, but the advantaged player is choosing simple moves. The advantaged player is always going to play simpler than complex in this sense, than the advantaged in this sense. And we've constructed equilibrium where it's strictly simpler. So in fact, sometimes the disadvantaged player is playing these risky moves, these Hail Mary passes, but the advantaged player doesn't want to do that. So let me give you a very quick sense of the forces involved here. If you're the advantaged player and you play a complex move, that's bad in a first order way because it increases the probability that you miss a blunder and you blunder and lose. So that's bad. But it increases the probability that the opponent blunders next period because you put him in a complex position. That's good. But it might not be very good because imagine, just for illustration, that we're in a case where the termination probability is 1 or nearly 1. Then as long as you don't blunder, the game is going to end and you're going to win after that. So there's really nothing to gain by making your opponent blunder. And so that gain could be small, and it's generally smaller for the advantaged player. Now, what makes the theorem not trivial is that the subsequent path of the game, what happens after that, is hard to control. Something happens and it's going to vary with all these parameters. But we can prove, the assumptions that we make ensure that the immediate bad outweighs the good, and dynamic considerations don't reverse them. Okay. So we think game theory doesn't have a great account as it stands for thinking about these decisions of whether to complicate people's decisions. Existing models like QRE, model response equilibrium and things like that, don't really certainly haven't thought about how players steer complexity when we can. We document some stylized facts about how that happens in this data-rich environment, and we propose a simple game theoretic model to study that relationship. Our model leaves an immense amount out, and I'll stop. But if you ask me about your favorite limitation of the model, I'll try to say what we're thinking with respect to that. We observe that in the data when people have the choice. When people have the choice without losing, while keeping the objective value of the game the same to complicate or simplify, they choose to complicate when we're losing, and we have some theoretical understanding of when that makes sense. And as I said, we would be delighted to discuss extensions in the Q&A if there's time. Thank you.